So in this video, we're going to learn a few new ways to make ketones and aldehydes. So we covered a bunch, right, during our last class session about reviewing some of these reactions to form aldehydes and ketones. So here's going to be a few more we're going to look at. So this first one is turning carboxylic acids into ketones. So when we have a carboxylic acid like this, we're exposing it to conditions similar to the Grignard, right? Where we have this organometallic compound here in two equivalents, and then acidic conditions afterwards. This grants us the following reaction, right? Where we are just connecting, right, the nucleophilic carbon here to the carbonyl, right? The mechanism for this is as follows. It is essentially where we are grabbing, right, that nucleophilic carbon is attaching itself to the carbonyl here, and we're getting this tetrahedral intermediate. And you notice that we are using two equivalents of that lithium reagent, right? The reason for that is just because, right, that carboxylic acid is pretty acidic, right? So the lithium reagent is just kind of there to make sure that we're actually progressing to the end. Because if we just had one equivalent, it would probably just deprotonate that acid here and not actually do the reaction in full. And then the next step, right, pretty easy. We're just pushing these electrons down, kicking off OH minus as our leaving group, and getting to our ketone at the end here. So the important thing to note, right, with this carboxylic acid organometallic reaction is that we need, right, these two equivalents of the lithium reagent. And the H3O plus there is to make sure things are neutral at the end, right? Because we do have O minus hanging around at the end, as well as potential lithium region left over. So for the next reaction we're going to look at some Grignard reactions again, actually. So we can make ketones and aldehydes from Grignard reagents as well. So if we have the following Grignard reagent with this nitrile here, right, the CN group, and we use the following Grignard reagents, H3O plus, we get to a ketone as our final product, just like with our other example here. So the mechanism for this problem is as follows, where we're having to actually attack the carbon of that nitrile. It's actually pretty good for an electrophilic group, because that nitrogen is pulling on those electrons, as it is more electronegative, right? And so over the course of this mechanism, which I'm going to draw next to the arrow, but I'll highlight the final product, we get this as our intermediate here, right, with that carbon down below, right, just went from writing it as C to just keeping it in the line angle structure, right, so our carbon is in that middle there, right, and the next step in this reaction, which we'll cover in a later video, the mechanism, because it's kind of a lot, we essentially go from this double bonded nitrogen to the ketone as our final product. And we'll learn about the mechanism later, but it's kind of complicated. The H3O plus is essentially protonating and removing the nitrogen over the course of a couple steps. But all we need to know, right, is that when we're going from the nitrile with these Grignard reagent conditions, we end up with a ketone at the end, okay? Another reaction we can do with these nitriles is something called a reduction, where once again we have our CN, we'll just do it like this, we won't put on the triple bond. These conditions that we're using this time is something called dibol, which we'll talk about more in a second here, and then H3O plus, we get to an aldehyde as our final product. Notice the number of carbons has stayed the same, but we still have 4 carbons, right? That carbon at the end here has just sort of become, right, this carbon. So we can go from nitriles to aldehydes. And that dibol species is something called isobutyl aluminum hydride 2. And we'll talk about that more in a second. But this is another kind of case of a sort of complicated reagent where all it's really doing, for the most part, is adding a source or it is rather a source of H minus in a sense, right, which allows this reaction to take place. And we won't worry about the mechanism for this because it is a little wonky, but you can imagine, right, the H minus doing something similar to the nitrile reaction we saw above, right? And so for the next reaction here, we can do this same sort of chemistry with acid chlorides and ester, right? And these are all ways to, ways to introduce H minus, right, hydride, as a quote-unquote nucleophile. Okay, where it's acting as a nucleophile and attacking these carbonyls here. So there's two ways we can do it, right? We do these traditionally with these bulky hydride givers, you might say. So we can do this with something called lithium tri-tert-butoxide aluminum hydride, which is this species here. We can abbreviate this as LTBA, and this is a way to get acyl chlorides, right, acid chlorides, to aldehydes. And we do this also in cold temperatures. Another way we can do this is with esters. And with esters, we can go from ester to aldehyde using similar conditions, but instead of using LTBA, we use something called, with this diisobutyl aluminum hydride. This is that dibol species. So dibol, or you can say dibol H, they all kind of mean the same thing. And this dibol species in particular is the following complex. This aluminum species with these diisobutyl groups coming off of it. And it's these really bulky reagents that actually, there's in truth two of them, right? So that should actually be two. There's two of them complex together, and it's just this really funky way to get hydride as a nucleophile, right? So we won't worry about that specific mechanism, but what we'll look at is a sort of general mechanism here. So let's look at this ester group addition, where we have dibol. We have to do this cold, right? So we have to do this at low temperatures as well. So when we say low temperatures, we actually also mean negative 78 degrees Celsius. So really, really cold. If it's too hot, it ends up doing more damage to the reaction. So we have that source of hydride, right? This dibol species, all this is really here is to add our H minus as a nucleophile. So that's all this is really doing, right? There's a little more going on than that, but that's essentially all we're really concerned about, right? Is this is allowing us to add hydride as a nucleophile, right? And so we get to the following intermediate here, this O minus species, and this is actually stabilized, and we'll draw in the hydrogen. So we get this tetrahedral intermediate, and it's actually stabilized by that aluminum species that is, right, kind of lost, quote unquote, its hydrogen. So this is sort of stabilized. So this is a stable intermediate, but still a tetrahedral intermediate. And just like we've seen before with Grignard reactions, it'll condense back down in the next step when we add H3O plus to get to our aldehyde. Right, with the H3O plus there, essentially to quench the reaction afterwards, because we have a lot of these negatively charged species kind of hanging around, right? So what we want to do, and aluminum should be positively charged, is quench the reaction when we're done, right? So that's essentially what's happening, right? We're going from esters to aldehydes with the introduction of this nucleophilic hydride here. And this reaction is essentially the same exact thing as the acid chloride, but instead of dibol, it's just LTBA. The same mechanism is taking place for the most part, okay? We don't really need to worry about drawing this in when we're doing this mechanism, but that's kind of just what's actually happening, right, quote unquote. So hopefully that makes sense. But again, these are just ways to, right, take these different groups and transform them into ketones or aldehydes.